So we have to calculate the horizontal active earth pressure. This horizontal active earth pressure is given by pH. pH is equal to half into Ka gamma h square, half into Ka gamma h square. Just put the values half. We have already calculated the value of Ka, that was 0.33, multiplied by gamma. Gamma is unit weight of soil mass, that is 18, and we have calculated the total height 4.75 square. Okay, there was some correction, I think. Here it should be square, 0.33 square, because this value is Ka square. Okay, by mistake I skipped that. Okay, just keep in mind that. Okay, so this horizontal active earth pressure, this comes out to be 67.688 kilonewton, 67.688 kilonewton, whereas this force, this will be acting at an height of, this. Okay, this will be acting at an height of h by 3. It will be acting at an height of h by 3 with respect to this overturning point or O point, Okay, so the moment developed due to this pH will be considered as overturning moment. Therefore overturning moment, this will be equal to pH multiplied by h by 3. We have pH as 67.688 multiplied by h is 4.75 divided by 3. So this overturning moment, let us consider this as m0. Okay, so this m0 comes out to be 107.17 kilonewton meter, 107.7 kilonewton meter. Now we will check for the overturning. Now we have calculated the resisting moment, at the same time we have calculated the overturning moment. Now we will check for the overturning. So check under this step number 3, check for stability. First check for overturning. Okay, check for overturning. We have already seen the formula for calculating the factor of safety for overturning, in this particular slide. Okay, you can see here. Yeah, this is the formula which is used for calculating the factor of safety for overturning, that is FS1. We consider FS1 as factor of safety against overturning is equal to 0.9 mr divided by mo, where mr is the resisting moment, and mo is the overturning moment. And this factor of safety, this should be more than 1.4. this factor of safety, this should be more than 1.4. Okay, so check for overturning. The factor of safety, for overturning, this FS1, we consider this as FS1, this should be more than 1.4. Okay, but we have the formula for calculating factor of safety for overturning FS1 is equal to 0.9 mr divided by mo, that is 0.9 into mr is resisting moment and mo is the overturning moment. We have just calculated the value of mr and mo. Mr was 256.6 and mo was 107.17. Okay, so this factor of safety, this comes out to be 0.9 multiplied by mr is 256.6 divided by mo, that is 107.17. so factor of safety, this comes out to be 2.15. This is more than 1.4 and hence okay. Okay, so this particular retaining wall is safe in overturning. Now we will check for the we will do the check for sliding. So B check for sliding. Check for sliding. Now we have factor of safety for sliding. Factor of safety for sliding, fs, let us consider it is denoted by fs2. This should be again more than 1.4. This should be again more than 1.4. And we have the formula for calculating the factor of safety for sliding, fs2 factor of safety for sliding is equal to 0.9 into mu, 0.9 mu into summation of w divided by ph. Okay, the formula is written somewhere here. Just a minute. Yeah, the formula is written here. The factor of safety for sliding is given by this particular formula, that is 0.9 mu summation of w divided by ph. This should be more than or equal to 1.4. This is the factor of safety for sliding. Okay, so just put the values. We get 0.9 multiplied by mu. We have already given the value of mu as 0.5, so 0.5 multiplied by summation w. We have already calculated the value of summation of all the resisting forces w in this particular step. Here summation of w was 163.33. So this, write down this value here, 163.33, okay, divided by ph. We have just calculated the value of ph, that is horizontal pressure which is acting on this retaining wall in this particular step here. So pH was 67.688. So this formula becomes 67.688. so we get this value fs2 equal to, we get this value fs2 is equal to 1.09. But you can see here, you can note here that this value of factor of safety against sliding, that is fs2, this is less than 1.4. This is less than 1.4, and hence it is not okay, or it is not satisfactory. It is not satisfactory, therefore not okay. Now we have seen in during the practice theory portion, if this particular factor of safety, the value of this particular factor of safety is less than 1.4, if it is less than 1.4, then some shear key is required to be provided like this. Okay, some shear key is required to be provided like this, which is given in this particular note here. If factor of safety against the sliding comes out to be, less than 1.4, then a shear key may be provided as shown in this particular figure. The shear key increases the resistance against sliding as the passive earth pressure developed on the shear key provides additional resistance against the sliding. Why we are providing this shear key? Because the factor of safety against sliding, that is fs2, this value comes out to be less than 1.4. therefore we need to provide some shear key, because this is your foundation ground. Again we have foundation ground on this side, we will have foundation soil here. So if we provide some shear key like this, concrete shear key like this, it will increase the resistance against sliding. Therefore for this particular case, as factor of safety against the sliding is less than 1.4, therefore we need to provide the some shear key. Okay, afterwards we will do the design of shear key. Okay, just keep in mind, as this factor of safety, as factor of safety 2, that is factor of safety against sliding is less than 1.4, therefore a shear key is to be provided to increase resistance against sliding. Okay, why we are providing this shear key? Because to increase the sliding resistance, as our factor of safety comes out to be less than 1.9. Otherwise, what you can do, if you do not want to provide the shear key like this, if you don't want to provide the shear key like this, just what you can do is to increase this base width, from 2.5 to let us try for 3 meter, whether this factor of safety comes out to be less than more than 1.4. okay, if it comes out to be more than 1.4, you can use as 3 meter, or otherwise what you can do is you can provide some shear key, okay, like this. Okay, better way is to provide the shear key from practical point of view, because if you increase the width of this base slab, it will result in lesser economy. Okay, so better is you provide some shear key. Okay, so up to this point we have done the check for overturning and check for sliding. Now we have to find out the pressure under the base slab. Okay, so step number 4. Step number 4 is pressure under base slab. Okay, now we know that there will be some overturning moment. About this point O. This is our point O, and there will be some overturning moment. All the moments will be acting about this point O. That is whatever moment developed due to pH, this will act like this. Whatever moments which are developing due to W1 will act like this, W2 will act like this. Okay, all the moments will be acting about this point O. Okay, so the final moment, okay, so we have to calculate the pressure under base slab. So final moment about O, this will be equal to resisting moment Mr minus overturning moment. Definitely resisting moment minus overturning moment. We have already calculated resisting moment as 256.6 kilonewton meter, and overturning moment we have calculated as 107.17 kilonewton meter. So we get final moment as 149.43 kilonewton meter. 143.43 kilonewton meter. At the same time we have okay, this is the final moment. Okay, and at the same time we have total vertical load, that is summation of W1, W2, W3 and W4, that is summation of all these forces. This summation of W is 163.33. so just write down here, we have summation of W is equal to 163.33. this value is 163.33 kilonewton. Okay, now the horizontal distance of point where resultant force will intersect with the base with respect to your point O, that we have to locate. We have already seen in some figure, I think. Here you can see some force pH is acting like this. This pH is developed due to the active earth pressure of your soil. pH is developed due to active earth pressure of your soil, like this. Okay, whereas summation of W, this summation of W is the sum of W1, W2 plus W3 plus W4. Okay, so summation, so due to these two forces pH and summation of W, some resultant force will also be some resultant force will be acting. Okay, now this resultant force will intersect or bisect the base here at some point. Okay, let us consider it is intersecting here at some point, the distance of intersection of this resultant with the baseline from the face of your retaining wall, this is called as eccentricity. Okay, it is called as eccentricity, and the formula for this is called as eccentricity, and this particular x bar distance is equal to this distance of this particular face of your retaining wall minus eccentricity. So we will calculate the value of x bar. And the formula for calculating the x bar is given by this particular formula, that is equal to mr, moment, resisting moment minus overturning moment, divided by your summation of W. So we will use this particular formula. To find out the value of this particular x bar. Okay, so we have this x bar. Okay, so x bar, this is, just a minute, I will draw the retaining wall again. This is our retaining wall. Base slab. This is base slab. Okay, this is our pH force. This is our summation of W. Okay, and resultant will be acting somewhere here. Let us consider it is acting somewhere here. This is our resultant force. Then this distance is eccentricity from the face of your stem. This distance is x bar. Okay, so this distance x bar, this is given by mr minus mo, that is resisting moment minus overturning moment, divided by summation of W. We have already calculated the value of mr minus mo equal to 149.43 kilonewton meter, divided by summation of W is 163.33. So this x bar comes out to be 0.915 meter. So we get this value is equal to 0.915 meter. Okay, then we can calculate the value of eccentricity. E is given by this particular formula. That is E is equal to B by 2, capital B by 2, minus x bar, not x square, it should be x bar. So we will use this particular formula for calculating the eccentricity. So we get this eccentricity is equal to capital B by 2, that is base width of your base slab, minus x bar. So we get this as 2.5 divided by 2 minus x bar is 0.915. So this is equal to 0.335 meter. So we have calculated the eccentricity E and the value of x bar. So this value is 0.335. Now we know how to now there will be some pressure which will be acting on this particular retaining wall from the ground or from the foundation. Okay, some upward soil pressure will be acting on this retaining wall like this. Upward soil pressure will be acting on this retaining wall like this, where we consider this value as P minimum, which will be acting at this hill portion, whereas P max is considered as the pressure which is acting at this toe portion, So we have to calculate the value of P max and P minimum, that is the upward soil pressure which is acting on this retaining wall. At the same time, we should keep in mind that the value of P max, this value of P max, this should be more, this should not be more than SBC, this should not be more than SBC, whereas P minimum, this should not be negative, this should not be negative, because if there is some negative pressure is developed here at the hill portion, this will fail by cracking, okay. So we have to calculate the value of this P max and this P minimum. So there are some formulas are already given for calculating the value of P max and P minimum. Just a minute. Yeah, these are the two formula which are used for calculating the value of P max and P minimum. The value of P max, and P minimum, these two formulas are used, that is P max is equal to summation W upon B into 1 plus 6E divided by B. So we will use this particular formula for calculating the value of P max, okay. So we get this P max, that is maximum pressure at toe end O, okay. This toe end O is equal to P max is equal to, formula is summation W divided by base width of your base slab multiplied by 1 plus 6E divided by B. Just put the values. We have summation of W as 163.33, base width of your slab is 2.5, 1 plus 6 eccentricity we have already calculated as 0.335 divided by base width of slab is 2.5. So we get this P max, P max is equal to 117.86 kilonewton per meter square, and it is more than, it is less than SBC, of 200 kilonewton per meter square, and hence okay. Okay, so we have got this value as 117.86 kilonewton per meter square, and now we have to find out the value of P minimum. The formula which is used for calculating the value of P minimum is this particular formula, okay. Only instead of this plus, just put the value, put negative sign, okay. So we get this P minimum, is equal to summation of W divided by B into 1 minus 6E divided by B, okay. So this is equal to 163.33 divided by B is 2.5 multiplied by 1 minus 6 into B, eccentricity is 0.335 divided by 2.5. So this P minimum or minimum pressure at the hill end, this will comes out to be 12.8 kilonewton per meter square, So this value P minimum, this comes out to be 12.8 kilonewton per meter square. So P max is 117.86 and P minimum is 12.8 kilonewton per meter square, okay. So this is how we have to calculate the upward soil pressure. At the same time, we have got this value as this is positive, and hence okay, this value should not be negative, this value should never be negative, if there is if it is negative, then your shear wall will fail, okay. Just a minute. Design of stem wall, okay. We have calculated this moment due to this particular force PH, that comes out to be 82.31, and therefore factor moment will be factor of safety multiplied by m, so that is 82.31. So factored moment, this comes out to be, the factored moment comes out to be equal to 123.47 kilonewton meter, 123.47 kilonewton meter. Now for we have to check whether the depth provided for this stem wall is sufficient or not. So for M20 concrete, we already know this depth is equal to, effective depth small d is equal to square root of mu divided by ru into b. We have seen this particular formula in the design of combined footing also. We can also simplify this for particular formula as mu divided by 0.138 FCK into b. Just put the values, we get mu is equal to 123.47 multiplied by 10 raised to power 6. Why 10 raised to power 6? Because we are converting it into Newton mm, divided by 0.138 into FCK. FCK is 20. 0.138 into FCK is 20 multiplied by b. Okay, we are calculating the values for 1 meter width of your retaining wall. Therefore the b will comes out to be 1000. The b will comes out to be 1000, that is 1000 mm or 1 meter. So this depth comes out to be, required depth comes out to be 211.5 mm, 211.5 mm. Okay, and we provided the effective depth capital D. We have provided effective depth of total depth of retaining wall at the base equal to 400 mm, and therefore let us consider some effect cover is equal to, concrete cover is equal to 50 mm. Then this effective depth d, small d, this will comes out to be 400 minus 50 mm. So this effective depth comes out to be 350 mm. Okay, and this is more than 211.5 mm, and hence okay, this is satisfying the depth criteria also. Okay, now we have to calculate the amount of steel required in this particular stem wall, steel required in this stem wall. Okay, we have calculated the bending moment, and now we have to calculate the area of steel required. Therefore area of steel required, area of steel reinforcement required. Okay, let us consider AST. We know the formula for calculating the area of steel, that is 0.5 FCK upon Fy, 0.5 FCK upon Fy into 1 minus square root of 1 minus 4.6 mu divided by FCK B D square into B into D. Just put the values. 0.5 FCK is 20, Fy we are using Fe415. So this formula will become 1 minus 4.6 mu. Factored moment is 123.47 into 10 raised to power 6 divided by FCK is again 20, B we are considering for 1 meter, that is 1000 mm, therefore B is equal to 1000, and effective depth is 350 square multiplied by B into D. B is again 1000 and D is 350. So we get this, AST is equal to 1041.92 mm square, 1041.92 mm square. Okay, so this is the steel required to be provided. Okay. Okay, now we have to check whether this particular steel required to be provided is more than AST minimum. So we get AST minimum formula for the formula for calculating the AST minimum is equal to 0.12% of cross sectional area. Therefore 0.12 divided by 100, cross sectional area will be 1000 for 1 meter, multiplied by, as we have our stem like this, here we have 0.2 meter top width, at bottom 0.4 meter. Therefore average width will be 0.2 plus 0.4 divided by 2. Therefore multiply this with 0.2 plus 0.4 divided by 2. So our AST minimum, this comes out to be 360, mm square, and it is less than AST provided, and hence okay, okay. Therefore we will be providing AST is equal to, provide AST is equal to this value, that is 1041.92 mm square. Okay, this much AST is required to be provided. Now let us consider we are providing some 12 mm 5 steel bars, okay. Then for 12 mm 5 steel bar we have to calculate the spacing. Okay, so provide 12 mm 5 bars, therefore spacing, let us consider S is equal to, the formula will be area of 112 5 bar, let us consider 12 5, area of 12 5 divided by AST provided multiplied by B, we are considering 1000 mm, so this will be area of 112 5 bar is pi by 4 into 12 square divided by AST provided is 1041.92 and width is 1000 mm. So this spacing comes out to be 108.54 mm, which is approximately equal to 100 mm. Okay, which is approximately equal to 100 mm. Therefore we will provide